Section 6.1 is titled The Set of Rational Numbers. And the first things we're going to take a look at is what that means when we talk about the phrase rational numbers. Rational numbers are fractions. They're any number of the form a over b, where b is not 0. A is called the numerator, and b is called the denominator, bottom of the fraction. Okay? Now, that's a description of fractions. Rational numbers is a little bit more specific. Rational numbers have this ability to be written as a fraction, but specifically, the a and the b are integers. Okay, so some of you may or may not remember what the word integers means. So if you do remember, can you give me what you remember about the word integers? What are integers? Okay, let's try a different word. Do you have an idea? Yeah, go ahead.
Are they whole numbers?
That's the next word I was going to say. That has this idea of whole numbers. So the numbers that you learn to count with, you know, like 0, 1, 2, 3, 4, so forth. There's something else that are integers too, though. The negative ones of those same values, right? So not all negative numbers, but the negative 1, 2, 3, 4, and so on. So they're positive and negative whole numbers in 0. Those are integers. So rational numbers have the ability that they can always be changed from however they start out looking to being able to be written as one integer on top of another integer. Now you have seen numbers that can't do that. You have seen the number pi, yes? Pi is not a rational number. Okay, it's about 3.14. Agreed? Okay, there's no way to change that into something that's an integer. It's not possible. So anytime in like geometry or trigonometry that you might have seen something like pi over 2, that is not a rational number. Okay? So it's not that you haven't seen those before, it's that those are not the ones we're talking about in this section. We're talking about the ones which can be rewritten to be integers, whole numbers, positives and negatives. Okay? Again, of course, we still have this condition, no zeros in denominators. That is not defined. We'll talk more about that one why later. All right, there are several uses of rational numbers. The first one is a solution. So for example, when you are solving equations, when you first start solving equations, you solve things where the answers are whole numbers, right? X equals 5. It's beautiful. It's wonderful stuff because it all works out so nice and neat. But eventually, you sound something like this. You're solving equations like 2x equals 1. Is x 0? No. Is x 1? No. If you put in 0, you get 2 times 0 is 0. If you put in 1, you get 2 times 1 is 2. It has to be something between 0 and 1. Well, if you only have whole numbers, there are no whole numbers between 0 and 1. So what is the solution to this if you have the ability to have fractions? 1/2. Or if you wanted to do it in decimal form, 0.5. Right? Without fractions, I can't solve this equation. It's not possible. It has to have a fractional answer or a rational number answer. The second is called partition. So we're going to give you an example of what that looks like. 1/4, that's a rational number, of my paycheck goes to buy gas. The whole is the paycheck, right? All the money you make. The part, the partition, the portion of, is a fractional amount of the whole. In this case, 1/4. Okay? We use rational numbers like that all the time. You're going to catch yourself now for the rest of today and tomorrow and the next few days. You're going to hear yourself saying things like this. It's a partition. The next one is a ratio. We use this one all the time as well. So I'm going to do one that you are bound to hear more and more and more as you go through your career here at OBU and then on into the workforce. The teacher-student ratio. Have we heard that before already? Mm-hmm. Is 1 to 8. Or you'll see it written in fractional form, 1 over 8. It's the ratio of teachers to students. Okay. The last one is probability. So for example, there is I'll do the dice example I have written down. I was going to try another one, but I'll give an example out loud on that one. There's a 1 out of 6, 1 over 6 probability of rolling a 3 on a standard die. All right, there's only 1 3, there's 6 sides, it's 1 out of 3 chance. This is what you hear used. They do it in a little bit different language, but this is what you hear used when the weathermen predict rain, right? They'll say it with percentages. But if there's a 60% chance of rain, that's a 0.6 probability. We'll talk more about probabilities in another chapter. But it's really a probability they're giving you in a percent form. All right, so the first thing I'd like for us to do is I want you to take a look at these diagrams. And I would like for you to write down the portion or the fraction that represents the shaded portion of this diagram. So just jot down what you believe the answer to be for all of them. We're going to double check and make sure everybody first has the right thing. And then we're going to sort of brainstorm what we think possible errors might be when our students see these problems and give us the wrong answer. Okay? So write down what you believe the correct answer to be for each of these first. After you've written 4 answers, turn to a neighbor and compare. See if they got what you got. And if you want to make corrections, either of you, that's totally fine. Okay, what did we get for the first one, for part A? What is that fraction? 1 out of what? 6. All right, so let's stop for a moment and ask ourselves, what do you think might be a possible error that a student would make if looking at this diagram? What might they say?
1/4.
They might say 1/4. If they said 1/4, why would they maybe say that?
We counted that whole section as 1.
Yeah, they might just be counting sections of what's there, right? So if you were to try to fix this diagram to help show a student why the answer is 1/6, what would you do?
Break up that bottom one into 3.
Yeah, so what's the goal when we're breaking it into 3? Why are we doing that? I mean, why do we want it to look like this to give us the 1/6 answer? I mean, what is it about this diagram that's more appealing than the other one?
It's more concrete than the other one was.
Okay, but
I
why?
can't physically count it.
There's 6 individual pieces.
Okay, what's true about the 6 individual pieces?
They're equal.
They're the same size, right? The issue is the size, so that makes it more concrete. We can see that the sizes match, and then the counting makes sense because the size of the pieces match. Now, part B has the same sort of problem. What's the right answer on part B? 1/4. This one's trickier than the first one, I think, even, but it's exactly the same problem, right? The answer the students might give is 1/5, right? This one's all broken up. I mean, I don't have any long sliver like I did on the first one. But what would I have to do to show a student what's really going on? I'd still have to do the same thing. I'd have to make the boxes the same size, right? And so perhaps a different color would help. Let me pick a different color. And instead, see, we've got this box right here that's this big, right? And if I take a look, this one right here, it's the same size, or at least seems to be. I would need that top box to actually have the same breaking apart so that I would have these 2 boxes right here. So if I ignore those 2 black lines that are sort of disrupting things, I have 4 pink boxes, right? All the same size, and now I've got 1/4 of the diagram shaded in. How about below? What do we have on C? 2 7s. Any thought about what a student might do that might not quite work on this? What they might give as an answer? There's a pretty good chance they might say 2/8. Because what object do you know gets cut into pieces like this? Pizza. And they might assume that they're looking at something that has been equally cut straight across, halved and halved again. So they might look at this and not really do the counting that they need to, and they might make an assumption that's not really there. How about part D? What is this one? 7/12. This one is somehow quite different than the other 3. Any idea what makes this one very different?
They're all separate.
Yeah. There's 12 separate objects, right? Whereas the other 3 are all this sort of big object that's been broken into pieces. That can confuse kids too, because it doesn't really look the same. It has a very different feel to it. We're going to talk about the different feel that that has in a moment here. A little bit of history first about fractions. Fractions have been used for quite a long time. The Egyptians used fractions. They always had numerators of 1. So instead of writing 7/12, like we had, I think, on our last example, they wouldn't write 7/12. They'd write it as a sum of fractions with numerators of 1. 1/4 plus 1/3. That sounds a little bit cumbersome to me, to write them all as sums. The Greeks adopted fractions with denominators of 60. Any idea what's special about 60? They adopted it from the Babylonians, by the way. Well, it talks about the measurement of angles. We talk in number theory, for those of you who've had number theory, about something else that comes with 60s. Do you remember what happened with 60s? What do you remember, Sydney?
The Babylonian number system was in base 60.
It was in base 60. And also, along with the idea of doing the measurement of angles, does anybody remember, or can you think about why 60 might be special? That's true. That's related to the idea of circles. Absolutely true. There's another fact, too, though, that's very interesting. Does anybody know, this is not the, does anybody remember the Mayan thing that happened a few years ago where everybody thought the world was going to end because the Mayan calendar stopped? One of the things that the Mayans did, and it's related to the Greeks here as well, is that they used a calendar. Do you know how many days their calendar had in it? 360. Why 360? Well, that's awfully close, right? I mean, ours is 365 and a little bit of change, about a quarter, right? Why 360? Well, 360 is so nice. It's 60 times 60. You've you've got all this beautiful symmetry involved. It's really nice. So all of that's sort of related to this idea, and so they were using 60 because it related to this kind of idea of our calendar, actually. Hindu, that's actually where we get our modern fraction bar. So the bar that we put between our numerator and denominator came about in use in the 1500s from the Hindu. All right. There are 3 models that we can use. This is related to the last picture that I just had up there, actually, for fractions. The first model is an area model. So an area model, it doesn't have to be done in terms of a rectangle, but it often is. It could be used, hang on a second. It could be used with a circle. That would be okay as well, but rectangle is the most common one. So if we had to do an area model for the number 3/4, how would I do that with a rectangle? What would I do? How am I going to break my rectangle up? Into 4 equal parts. The denominator tells me how many equal parts I need, right? So maybe I'll do something like this. Here's my 4 equal parts. Or maybe you want to do 4 all vertical equal parts. That's fine too. I don't care. Okay? And then what would I do? Shade. How many would I shade in? 3, because that's the numerator. So there's 1, 2, 3. That is the fraction 3/4. A number line model is another model. I didn't have an example of this one earlier, actually. It's another model for how we can represent fractions. So in this one, we have a, if you will, a beginning and an end. So we'll call this 0 and we'll call this 1. And 3/4 represents how far along the number line that we get toward the number 1. So because it's so nice, we can partition it much like we did the last one. I partitioned it into halves and then into fourths. So the 0 actually represents 0/4. The first hash mark would be 1/4. This one would be 2/4, which we could reduce. And this one would be 3/4. And then I've got my whole number 1. So on a number line model, this represents the number 3/4. You will also sometimes see it drawn in like this. Just say that that length represents 3/4. Either one is an acceptable way to interpret that model. The third one is the set model. So the set model has some limitations that the other ones don't. It uses chips. So we create, if we're creating the model, it's easy enough. The denominator tells me how many of the object we create. So we're going to create 4. So we're going to create, that wasn't what I wanted. Let's try that again. 4 chips. They should be all roughly equal in size, so ignore the fact that mine aren't perfect. And then we're going to shade in however many we have of those 4. So that would be 3 in this picture. So here's 1, 2, 3. 3/4 of the chips. That works fine if we get to control how many chips we have. The problem comes into play when you're already given the chips. So what happens if you have 5 quarters? Like the coin, 5 quarters. And you want to divide them somehow evenly between 3 children. Or you want to know what is 3/4 of those 5 quarters. It doesn't work very well, does it? It really only works if I get to decide how many quarters I have to start with. So it does have that sort of weird limitation to it that the other ones don't. All right. Fundamental law of fractions. In mathematics, anytime you hear the word fundamental, it means it is very important. Okay? This is the fundamental theorem of fractions. Fundamental law of fractions. If you have a fraction a/b, any fraction, so it doesn't even have to be rational numbers, but any fraction, and you have a number n, non-zero integer. Okay, so we can't use the number 0. That one won't work. But any other integer will work just fine. And it's actually true for any other rational number, not just integer too. But if you have that n and you multiply it on the top of the fraction and you multiply it on the bottom of the fraction, the value of the fraction does not change. And you guys have used this hundreds, if not thousands of times. We use it to find common denominators, to add fractions together. We use it to find common denominators to compare fractions to one another. All right? It's usually used for some reason to make denominators match up. Right? Simplest form is a version very much like the, it's a description very much like the fundamental law. It says that a number a over b is in simplest form if the b is greater than 0, okay, so the denominator is positive, and the greatest common denominator, GCD means greatest common divisor, GCD. The greatest common divisor of the top and the bottom is 1. So in layman's terms, what does it mean? Well, it means that I can't reduce the numerator and the denominator by the same value. So for instance, if we were working on the top and we started out with the number, say, 3 out of 4, because we did it just a moment ago. And I multiplied the top and the bottom by the same number, so just for fun, we'll multiply it by 5. I would get 15 over 20, right? That's fine. Got 15 over 20. Is 15 over 20 the same value as 3 over 4? Absolutely is the same value. But 15 over 20 is not in simplest form, and 3 over 4 is. So why is 15 over 20 not in simplest form? It can be reduced. 15 and 20 have something in common, right? They have a common divisor, 5. 3 over 4 is in simplest form. There's nothing that will divide both of them except for 1. Their greatest common divisor is 1. So these two, this definition and this theorem, they go hand in hand. They're exactly the same thing. They're just stating it in a different way. All right, we're going to do an example. We're going to create 3 fractions that are equal to 7 over negative 14. So I want you to write 3 down, any 3 you like. And then I will take some suggestions from you and maybe add a couple of my own as well. Any fraction at all that's equal to this one. All right, somebody give me a suggestion. What'd you write down? Just one. Give me one. One of your paper. Okay, what do you have?
1 over negative 2.
1 over negative 2. All right, somebody give me another one that's not this one.
2 over negative 4.
2 over negative 4. All right, we'll do one more. What's another option you guys thought of?
3 over negative 6.
Okay. Whoops. That was a little too long. Okay. So let's talk about the first one, and then I'm going to add a couple to this in a minute. How did you get the first one? What did you do? Reduced. Okay, divided by 7 on the top and 7 on the bottom, right? And then how can you get the next 2 after you have that? How do you get 2 over 4 and 3 over 6 when you already have 1 over 2? You multiply the top and the bottom by the same number. That's that fundamental law, right? Okay. Now, you don't necessarily have to reduce this to begin with, did you? Did anybody not reduce the 7 over 14 and so their answers were bigger? What'd you have?
I derived the bigger of the first two. I have negative 21 over 42, negative 14 over 20.
Okay, I'll just write down one first of them. Okay, so how did you get the negative 21 over 42? There's actually 2 things you did, so tell me what you did to get the numbers.
Multiply the top and multiply 3.
Okay, so if you multiply the top by 3, you get 21. You multiply the bottom by 3, you get 42. You also did something with your negative that I'm glad you did. What'd you do?
Added it to the thing.
You put it either in the front or on the top. Does it matter where the negative is? It doesn't. So this fraction right here is equivalent to this one right here, right? They're exactly the same. It doesn't really matter where the negative is. These are actually different fractions though, aren't they? They're the same value, but are they different fractions? They are, because the negative is on the numerator 21 or the negative is on the denominator 42. Okay, awesome. All right, the next one we're going to look at is a little different. We're specifically told to find simplest form for this. But what about this one looks a little funny?
Squared.
The squareds. you cannot just mark the squareds out. Squaring the top, squaring the bottom, it's not the same thing. So we can't just sort of mark them out like we can reduce that. We can't do that, in fact. So for the moment, let's ignore the square. We're not going to ignore it forever, but just for the moment. Let's take a look and think about the 42 and the 35. Just think about those. If you just had 42 over 35, what might you do to get that in simplest form? Divide by 7. Fabulous. So if I had 42 over 35, and I divided both of them by 7, I would be able to reduce what I had. But I don't really have 42, I have 42 squared. I don't really have 35, I have 35 squared. So instead of the dividing by 7, I'm just going to write the 7 here. What is 42? 7 times what? 6. Good. And all of that is squared, correct? What about the denominator? What is the 35? 7 times what? 5. Now very quickly we're going to get into some properties of exponents and so forth, but squaring means multiplying it by itself. So if I have 7 times 6 squared, it means I have 7 times 6 times 7 times 6. Is everybody with me on that? And 7 times 5 means 7 times 5 times 7 times 5. So I am going to reduce the 7, but I'm going to reduce it twice because the number was squared. So I have the 7 here and the 7 here that reduce. What does that leave me with on top? 36. 6 squared, or 36. What does it leave me with on bottom? 25. Some of you are thinking, I don't think I should leave it that way because the top is bigger than the bottom. That's okay, all right? Unless the problem tells you not to leave it in that kind of a form, or unless the problem started out in what would be called a mixed number form, then it's perfectly fine to leave it like this. There's nothing wrong with that. This is the reduced and simplest fractional form that this can be written in. Is that good? I don't know about you, I'm all about not having to go through any more work than I need to. So this is a good thing. All right, theorem 6.2, equality of fractions. This theorem says two fractions a over b and c over d are equal if and only if a times d equals b times c. And you've probably seen this drawn out like this before. You've either seen somebody mark it like that, or maybe you've seen somebody circle it like this. I had a student one time that told me they learned it as a butterfly. It's like a butterfly. Whatever visual imagery you need, what you're doing is you're multiplying the diagonals together. So if these are equal, then it will be true that a times d is equal to c times b. But the cool thing is that it's also true that if the a times d is equal to the b times c, then the first two are equal to begin with. It's an if and only if. It works both ways. So I can check to see if fractions are equal by doing this sort of cross multiplication thing and checking it out that way. And that's very handy. Does a times d equal c times b? All right, so this is just one of several ways that we can check to see if fractions are equal. So the first one we're going to look at is kind of some big numbers. We have 3 over negative 12 and negative 36 over 144. And we are trying to decide if these are equal. Now, the first thing I'd like to say is since they're both negative, I'm going to ignore the negative. Okay? I know that part matches. So it's really the numbers I care about, not the negatives. So as I do the whole problem, I'm going to ignore the negatives from the get-go because I know that part matches. So the first thing we're going to do is we're going to do it the way that the last slide told us, which was Theorem 6.2. So Theorem 6.2 says that if I compare the fractions, I'm asking myself, this is a question mark, are they equal? I don't know if they're equal. I'm trying to figure it out. Does 3 over 12 equal 36 over 144? And so how do I decide? Well, I do this sort of fun butterfly thing, right? I check it out like this. So if you have a calculator, go ahead and grab it with you. If you don't, just bear with us and look on with a neighbor. we're asking ourselves, does 3 times 144, is that equal, question mark, is that equal to 12 times 36? So what is 3 times 144?
432.
432. What is 12 times 136?
432.
432. Are they equal?
Yes.
Yes. Oh, if I write it right, they will be. How about 432? Yes, they're equal, which means the original fractions are equal as well. Okay? So the answer is yes. They are equal. It says way to do it number 1. Does anybody know any other ways that you might try to do this?
Reduce 36 over 144 is 3 over 12.
Okay, so what would I have to divide by to check that out?
12.
Okay, so I could do something where I reduce. And I could reduce one or both. I'm just trying to see if in reducing something, I end up with matching items, right? So looking at the 36, again, ignoring the negatives, the 36 over the 144, if I divide them both by 12, 36 divided by 12 is 3. 144 divided by 12 is 12. And this equals the 3 over 12 that I started with, right? So they're equal. Okay, anybody else have a third idea? Maybe I should clarify why I'm asking for this right now. It doesn't matter which one you use, but sometimes one is better than the other ones depending on the fractions you're working with. The first one that we did, the first option, Theorem 6.2, works really well when numbers are kind of small, but if the numbers are really large, I don't know about you, but if without a calculator anyway, I wouldn't want to multiply the numbers together in every situation. So reducing might be more practical, especially if, what if you looked at these numbers to begin with and you saw 36 and 144 and you knew your 12s tables? That's probably going to be a faster way to do that problem, right? Yeah. Does anybody think of another way to check these? You got it. All right, so there's 2 ways to do this with common denominators. One of them is called least common denominators. And the other one is just called common denominators. Okay, so I'm going to do the least common denominator way first because that's probably the one that you're most familiar with having seen before. So if we do a least common denominator, what we're looking for is we're looking for a way to compare these numbers together. We have 3 over 12 and 36 over 144. And what you're really looking to do is you're looking to see if you can take the 12 and the 144 and get the smallest thing they have in common. Well, it's going to have to be at least as big as 144, right? Because 144 won't have anything in common multiple-wise if it's smaller, so it has to be bigger. And you recognize, probably, that if I take the 12 and I multiply it by top and bottom, kind of like I divided it by top and bottom just a minute ago, that very quickly I get the 36 over 144. Right? That is the least common denominator. Now, that's all well and good if you look at it and you know what the least common denominator is going to be. But sometimes you don't when you look at numbers. Like you may notice they have some things in common, and you may notice that they don't have this ability to just multiply one of the numbers by something and get the other one. Okay, so what I'm about to show you is absolutely not at all practical for this problem. Everybody okay with that? I'm showing you something impractical for this problem, but it is practical for some problems. So what can you do? Well, to find a common denominator in general, what you do is you multiply the 2 denominators by one another. So you multiply the 12 by 144, top and bottom. And you multiply the 144 by 12, top and bottom. This is an efficient way sometimes to do the problem. It's not very clean. Like I end up with bigger numbers usually when I try this, okay? So somebody tell me, what is 3 times 144? Something large. 432. What is 12 times 144? It's even bigger.
1,728.
Excellent. What about 36 times 12? 432. And then the 144 times 12 we already know is 1728. Because we already did that one. And lo and behold, the answer at the end, they're equal, right? So if the fractions we get at the end are equal, then the original fractions were equal as well. Again, not practical for this problem. But sometimes it's a lot easier to do than try to find the smallest thing they have in common, which is not really what you cared about to begin with. You just cared about comparing. Right? All right, Theorem 6.3 goes right along with Theorem 6.2. 6.2 told you how to decide if fractions are equal. Well, this one does the same thing, but it does it for inequalities. So if you have a fraction a over b and that fraction's greater than c over d, you can still do this cross-multiplying business. And if the a times d is greater than the b times c, then the original fraction's direction was the same as well. So let me write that down the way I drew the picture on the other one. So we're still multiplying these two together, we're multiplying these two together, and we're keeping the direction of the inequality the same. So you do have to start in the top left-hand corner to make sense of this, right? It matters. And then you end in the bottom left-hand corner. C times D. C times B. That's a typo, I'm so sorry. C times B. Or B times C if you prefer. Okay, this is the same thing though, right? The only thing to be careful of is the inequality's direction itself. Okay, this is the same theorem really. All right, so let's actually take a look at another example. This one we're going to arrange these in ascending order, and it does not ask us to do it in a specific way. We can do it however we like. Now, the catch is there are 3 of them, not 2 of them, right? Because of that last theorem, 6.3, is probably not very practical to use because it only compares 2 fractions at a time, and I want to compare all 3. So we've talked about how to compare fractions. I mean, basically, that's what this slide was all about. There's 4 ways to compare the fractions to decide if they're equal or greater or less than. These are the 4 ways. Which one might be a good choice for this?
Least common denominator.
Yeah, I think a least common denominator would be very friendly, especially because the fractions themselves lend themselves to that, don't they? Look at those denominators, 20, 5, and 10. Do you see what the least common denominator is going to be by looking at them? 20, right. All right, so the 13 over 20, I don't really have to do anything with it, so I'll just write it down for the moment. Let's take the 3 over 5. What would I need to do to get this one to have a common denominator from the first one? What would it need to be multiplied by? 4 over 4, right? So if I multiply this by 4 over 4, what do I get? 12 over 20. So we'll come back to the putting them in order in a minute, but we've got the same denominator now. We've got one more. We have 7 over 10. What would I need to multiply this one by? 2 over 2. All right, so if I multiply 7 by 2, I get 14 over the 20. What does the word ascending mean? Gets bigger. Good. It means it goes up, right? When you ascend, right, like on an escalator, you ascend, you go up. Where we talk about Jesus' ascension, he's taken up, right? Ascend. So we want to go from smallest to largest. So which one of these is the smallest? I'm going to number them. The 12 over 20, that's my smallest one. Which is the next one? 13 over 20. And the last one? The 14 over 20 or the 7 over 10. Now, our answer needs to be in the way that the problem started out. So as a general rule of thumb, unless you're told otherwise on a problem, your answers are always the same notation that you started with. So what is my smallest one? Well, it's 12 over 20, but I want it written originally. It was written as 3 over 5. You can put a comma, or if you want to put a less than sign to indicate it's getting bigger, that's awesome. What is the next one? 13 over 20. And then the last one, 7 over 10. And again, I don't care whether there's the less than signs. You could certainly put the commas between them, and that would be fine as well.